So welcome to the presentation today. So we are tackling today the ecological aspects. So from CMOS Fabrication to Advanced Packaging. Myself, I'm Michael Schiffer, the head of the department Wafer Level System Integration. And my co-host today is Violeta Prodanović. She's doing the business development for the department. And the presentation is meant to tackle a lot of topics regarding the eco aspects in those fabrication systems. We are not going deeply into specific topics. We are more giving an overview, including cleanroom technology, including process technology, including eco indexes for the complete process chain. So let's start. And now it's not working anymore. So you can see, I will start with the semiconductor production, just a roughly introduction to that. Also the cleanroom environment aspects, dealing with the cleanroom classes, operating conditions, the air handling, water purification, etc. We will then go more into the chip production, environmental data indicators, electricity consumption, water consumption, recycling. There we have usually data from large companies as far as they're available. Then we are going into carbon footprint of front-end manufacturing packaging technologies. And then we will end the session with some process-related details, especially there are some topics that are valid for both, so front-end and packaging, but there are also some processes that are more relevant in one of these domains, and then we will conclude the session. So we start with semiconductor production. So when we have the fab construction, so this is the Infineon fab in Dresden, where they have done the groundbreaking in spring 2023. So when you build such kind of a fab, you look what are the fab infrastructure requirements. So you will look for that you have large plots of land, because you will probably need more space afterwards, or you have to have different buildings not close to the fab. You want to have low seismic activity. That's, I think, in the case of lithography, quite clear. You will definitely need a stable water supply, because this is one of the major concerns for large fabs, especially for the surrounding of such kind of fabs. We need the stable supply of electricity. You need talents. Depends on what kind of advanced node you are fabricating. It's more valid or less valid in that case. But anyhow, you need some kind of attractive surrounding around your fab that people will come to you. And you will need a lot of transportation infrastructure because, yeah, clearly you need material going in and out. When we are looking for the German landscape, sorry for the people that are coming from overseas, but I will come on the next slide to that. We see roughly, so this is not a complete list, but we see roughly these kind of companies, and they are distributed all over Germany. We have some clusters around Dresden, where we have a lot of CMOS fabs like Global Foundries, ESMC now, Bosch, X-Fab, Infineon. And then we have more in the south of Germany, other companies that are also working in that range, but not too much in the CMOS area. This is just a list for, just to demonstrate how far we are sketched in Germany. The companies in the south are more not CMOS focused. Maybe some are also only focused for different semiconductors like silicon carbide, Wolfspeed, for example, or TDK for our devices, Osram for photonic or LED devices. So we have quite a lot of ecosystem here in Germany as well. When we are now looking for the worldwide production, and there we look first on the left side to the wafer fab capacities by fab type. So this is only concentrating on technology nodes below 45 nanometers, just to get not too much data into that. This data from 2020. And when you look in let's say Germany, Italy, and others. So maybe we are more or less, or here when we say European fabs or European manufacturers, we are not very well visible there. In some areas, we are not visible at all. In some areas like analog chips, we are more visible. I think that indicates also in some kind what technology or what kind of application we are delivering in. But it clearly shows the lag that Germany or most of the other European states have not that advanced node systems. The advanced nodes are really clearly focused in America, in Taiwan for sure, South Korea, some in Japan. So there we have really to keep up if we want to reach 1/3 of the production there. On the right side, you can see that the global semiconductor production is still rising. This is from a study from 2023. They more or less dealt with these companies because they could get the data from the reports so the financial reports and also CSRs that are or that were enough to generate the data for this graph. And you can clearly see that in TSMC is still leading. So this is not a linear axis. But you can also see that some of the companies are more stagnating. Some of them are going higher and higher. But in overall, it shows really that more and more companies are going or are building more fabs, especially now with all the CHIPS Act programs around the globe. So more and more fabs are built, and therefore we really have to carefully look on the eco aspects there because such kind of fabs are quite problematic in some cases. So you have to deal really with a lot of materials there that can be harmful to the environment if they directly go into the environment. So let's look a little bit closer to the cleanroom environment. So what do we have there? What we can really look into, especially when it comes to energy, water, and gas supplies. So let's start first with the classes. So when we're talking about the cleanroom classes, these are needed because these are just some examples in comparison to human hair. So the human hair is something in the range of 60 to 80 micron thickness. We are here at Fraunhofer IZM, we are working in the packaging area or wafer level packaging area. So there we are going down to sizes between 1 and maybe 10 or 20 microns, like shown in these. So the middle picture, gold bumps, the bottom picture are just some copper lines, very fine copper lines. When I bring them in perspective to the human hair, you can really clearly see how small we are. And that is the need for the clean room. We need also for the packaging there. Here's some old pictures of the first clean room Zambia National Labs. And as you can see, in the early days, we went with suits in the clean room. So typical office space is around ISO 9. With the first clean room was ISO 6, which corresponds to the old standard, the FED standard around class 1000. Usually when we are on the wafer level or in the front end area, we are going in the range of ISO 5 down to ISO 1 in some extreme areas. And as you can see here, what are the requirements regarding particle sizes? It's quite harsh. So for our case, in our institute, we are in the range of ISO 3 to ISO 5. Most of the labs are ISO 5. So you see that we have quite some particles that are in the range of those copper lines. In some areas, like in lithography or where we need this cleanliness, we go down to ISO 3, so class 1. And there you can see we don't have that many large particles there anymore. So Let's go to the operating conditions in a clean room. We have approximately 45% relative humidity. Depends a little bit on the process requirement and the area we are working in. Temperatures around 21 degrees C. Cleanliness is smaller than ISO 5 in the white zones. We have an air pressure or overpressure of approximately 10 Pascal and an air circulation of approximately 0.4 meter per second. That is valid 24 hours per day, 5 days per year. So there's very, very extensive infrastructure needed with quite some high energy requirements. When we're looking at our clean room now, so the yellow areas are the clean room that is dedicated to any kind of wafer or fine pitch assembly topics. So in this area, we have the wafer clean room. Here we have the assembly clean room, approximately 1,000 square meter netto area. And then what is very important for us as well is the clean room facilities here. So this is a very old drawing, but in principle, it's still valid for our site. So we have the facilities concentrated in this area. When you look with Google pictures on our floor plan, we have approximately here in this hall the clean room for the wafer level packaging, and here we have the facilities. So when you say facilities, what do I mean with that? So a lot of that is the air handling. So we have the air supply, air exhaust. The air is supplied to the clean rooms, to the gray room area, depending on the cleanliness level with different filter fan units on top. We have the ultra pure water supply, which is in this region. So as I said, these are old pictures. Today they are a little bit larger because the clean room grew over the years. It was built in 1990. It grew over the years quite significantly. I think we doubled the size approximately. We have the process gas supply and the process water neutralization. So when you're looking at that, one of the biggest impacts or one of the most needed supply is the air handling supply. And when you're looking to building such kind of a clean room, there are different possibilities how to do it. It really depends on the clean room class you need. I just took here a cross-section of a modern clean room, how it's built today. So we have the clean room area here in the yellow part. In the areas where you need no particles or to minimize the particles, you have specified filter fan units over there. Otherwise, you have the filter fan units all over the ceiling. You have in a second floor underneath, you have all the air handling, the pressure pumps, etc. And then in the basement, you usually have the chemical handling. But as seen here, you have also the air handling system from top going through the filter fan units, then through the clean room, through the floor, and then back again in the air handling system. And you have also scrubbers in areas you need that, where you will do the abatement of different harmful substances. So in principle, we have multiple filter stages for the outer air until it gets into the clean room. To minimize the energy consumption, you will also mix, let's say, used and refreshed air with fresh air from the outside. You have precisely to control the temperature, humidity, and especially for the exhaust, you have really to clean all the air that has been gone through any kind of plasma treatment or plasma machines. As well, for the water, you have to take care of acidic, alkaline, VOC containing, toxic, etc. So this is all in the infrastructure of the clean room. When we are looking for the different classes, so here I have 3 slides on that, and I go fast through that. We have different classes here, the let's say worst classes, at least on the right side. We are in the range of ISO 8 corresponding to class 10,000. You have no double floor. You have only one primary alone handling system for you can have some extra units to have a lower class in certain spaces, but this system is really limited, and it really depends on the size of the rooms, how you can configure your fab there. When you look on the right side, this is just a schematic of the same system on the left. But what is more important, you have to see what is the CFM per ton ratio, so the cubic feet per minute per ton. And this is approximately, rule of thumb is if you have 400 cubic feet per minute per ton, describes that every ton of cooling capacity you provide, you get out 400 cubic feet per minute of airflow delivered to the space. And we will see in the next slides, the better the clean room class gets, the higher those numbers get. So for the next one, this would be something like we have here at the Fraunhofer, where we have a double floor, we have HEPA filters on the top side of the clean room. We have primary and secondary air handling systems, so we can really reach ISO class 5 plus minus 1, I would say. HEPA filters are usually rated for ISO class 5, and they 99.97% efficient on 300 millimeter particles. So smaller particles are still going through there. But there you can already see with the CFM per ton ratio that it goes up 5 to 10 times of that of a very simple clean room like the last slide. If you go now then to the highest ISO classes, so 1, 2, 3, 4, you have now 3 stages of handling systems until it gets in a clean room, and there you have ULPA, no HEPA filters anymore, you have ULPA filters. ULPA filters are usually rated general class 3, and there are nearly 5.9 efficient on 100 nanometer or 112 nanometer particles. And there you can see that even there, the CFM per ton ratio is really now skyrocketing. So you have to really carefully decide when you build a clean room, what are your needs? Because you will not build a clean room only with class 1 and 10 because it's so expensive, and also the energy consumption is quite a lot. And in such kind of systems, when you have complex air supply here, you will see that you also have the return air that will go into the fresh intake in several stages. So to really minimize the fresh air you have to take out from the outside. Yeah, when we talk about air handling system, we're not talking about only the supply, we're also talking about the exhaust treatment. I will not go too much into detail here, but basically for all those, let's say, wastes you cannot directly pump in the outside, you have different stages and different machines that will do the abatement of them, and then they can go in the outside. So the effect of large exhaust volume, you will also minimize those if you like, because the system can only provide a certain amount of that, and you want to minimize that to save the energy. So most effects for the exhaust is high demand for fresh air to be supplied and treated. So therefore you have the recycling cycles that you not only take in fresh air, you have a larger dimensioning of the exhaust air system to be able to also treat some peaks in your fab. And you have to deal with low concentration of pollutants to see how effective your cleaning is. Measures to reduce now the exhaust volume would be reducing the exhaust capacity. When the system's on standby, for example, if you don't have a 24-hour shifting system, you can go into night shift or night or reduced airflow in the night. Or you can have something like self-regulating dynamic controls in process areas that are allowed to do so. So let's say when you use the machine, then the exhaust goes on, otherwise it will stay minimized. You will have also, or you want also to have the exhaust and abatement machines near to the process machines, that you don't have all the toxic exhaust gases going through the whole fab. And you will also look to change over to other process chemicals if possible, that the exhaust treatment is not that intensive anymore. So when we go to water purification in fabs, you can see that most of the water is going in the process water. It's nearly 3/3. The rest is going into either cooling towers, scrubbers, so abatement, let's say, kitchen and toilets and others. There are 4 types of water that are used in clean rooms. However, for the CMOS production or for very low particulate water, you want to go for deionized or ultra pure water. However, these 2 water types are needing most of the treatment. I will have on the next slide the ASTM standard for different water types, and you can see that water type E has different levels, water type E1, I have to say, and they also directly say what kind of line width they see possible with that. So in our case, we have water quality like this. So we have 18 mega ohm resistivity. We have a low oxygen dissolved here. Residues of after evaporation also very low. But you can see that also E2 and E3, E4 for larger line widths or for, let's say, substrate manufacturing or something like that, there you can go to different water types, but for very high quality wafer processing, you have to go to one of the type E1 waters. This is a system for ultra pure water generation, how it looks like today. Usually you have 3 stages where you have tanks, and you can usually also pump from one stage to the other, to the lower stage to circulate the water. So you have the intake water, you have different filter stages and softeners, and then you have basically 2 reverse of osmosis types before you go into the electrodeionization system, which takes quite some energy. Then you have again a tank now where you store that water, and then you go to several stages for purification or for polishing, for degassing, and then in the end you go to ultrafiltration, and then you go to the clean room so that you have really the highest quality of water. What you're looking also in such kind of clean rooms, that you can also reclaim the water again. So this is a very, very hot topic for large companies because they are limited in the intake water amount. Otherwise, the cities around them cannot survive anymore. And the other point where people are looking right now is to generate energy savings when they go for different deionizing methods like capacitive deionization instead of electrodeionization. So with that, we go to the water waste treatment in semiconductor companies. And there you can basically assume that most of the very, very concentrates you will treat separately or you will collect separately and then go for recycling or disposal. If you have contaminated water, then you go through the neutralization. Some parts of that are also going to waste or recycling. Otherwise, going to the indirect discharge of wastewater. And then you have different rinse waters, like organic contaminated, inorganic contaminated, or without any chemicals in it. And they will be either go directly, like here, after quality check again into the ultra pure water generation, or you have to clean them up and then go into the neutralization and then in the waste or in the indirect discharge of wastewater. So let's come to Violeta. Please take over.
Yeah, thank you for handing over the torch. So I will start. Yes, I will start by saying a bit about the environmental indicators used in semiconductor, well, in general, but in this case in semiconductor industry. So the most important three ones which do not give the complete picture but do give a pretty good overview are energy consumption. A little bit more informative than that is the primary energy demand, which also contains information on the conversion and transmission efficiency of electricity generation. Water consumption, of course, a total amount of water intake and recycled water, and then global warming potential, which is usually quantified in kilograms of CO2 equivalent. Greenhouse gas emission protocol differs three scopes of emission. Scope 1 would be direct emission from owned or controlled sources. Scope 2 is stemming from the generation of purchased electricity, steam, heating, and cooling. And then Scope 3 refers to emissions from the corporate value chain. This one is usually the most challenging one to be quantified. And as I will show in a bit, Intel seems to be one of the few companies who is doing a pretty good job on that one. So the ICT footprint is estimated to be somewhere in between 1,200 and 2,200 megatons of CO2 equivalent, according to the data from 2020. Between 360 and 660 megatons is attributed to the production. This, however, is not really matching the data on this device level. So a group of authors was looking into the carbon footprint of a phone, where it turned out that the production is actually contributing with 70% to the overall carbon footprint. So how is data collected? Usually we heavily rely on corporate sustainability responsibility reports issued by companies annually. And on the right side, there is an extract from Intel's report, which goes into details about Scope 3 emissions. From this enterprise, another source of data is our roadmaps, though of course they usually do not give guidance and targets, but do not provide the measured data. The most famous one is ITRS. Of course, there are peer-reviewed scientific papers, and another source of information are life cycle assessment databases. The most famous commercially available one is EcoInvent. However, it is very difficult to have a complete and up-to-date LCA database. There are multiple reasons for that. So the technologies in ICT industry are changing very rapidly. There are so many stakeholders involved then in the overall supply chain, and also there are confidentiality issues and challenges which are related to the IP. A little bit more on the energy efficiency in the chip production. So this graph on the left shows the data which is collected from CSR reports of a few companies, TSMC, SMIC, Global Foundries, UMC, and ST Micro. And we noticed that there is usually the same set of foundries involved in papers from different authors, which probably means that they are reporting on their environmental impact in the same manner. So it's somewhat easier to extract conclusions out of those reports. So the companies usually, of course, do not go into details what kind of mixture of technology nodes they have, but from CSR and financial reports, we can extract the data over the years, in this case from 2010 till 2020. And there are two trends that can be noticed. The first one is related to TSMC, where the primary energy demand is constantly increasing. From this sharp rise in year 2019, we can conclude that that's the time when TSMC announced the 5 nanometer technology. When it comes to other foundries, it can be seen that indeed the energy efficiency improved, so the manufacturing processes have been optimized over the years. Of course, that can be reached if the company is not heavily focusing on implementing more modern technology nodes in the production. We also try to figure out what is this sharp change that happened at Global Foundries around 2015. It could be that around that time the company decided to focus more on the older technology nodes. Though it's not in some press clippings. It has been announced by TSMC that EUV related processes are consuming almost 1.5 more electricity compared to, I quote, mainstream technology nodes. And yes, EUV tools use 10 or more power compared to DUV. On the right side, there is a graph which represents what portion of electricity in a fab environment is being spent on different processes. Most pronounced ones are, of course, processing tools, water chiller, and then, of course, there is CDA processes and generation of ultra pure water. I'm trying to change the slide, but it's moving very slow. Okay. Related to water consumption. So this is not too much technical content, but still a very interesting situation to report on, and how farmers in Taiwan are being affected by having high-tech people as their near neighbors. So TSMC in this case, I think in 2021, the heavy drought happened in Taiwan. It happens somewhat frequently as it is a region with high water scarcity, and so the government of Taiwan is having these 5 levels of water indicators or messages, if you wish. The first one, when everything is normal, nothing changes, but then already at the second one, out of 5, farmers are encouraged to produce less or to stop producing. And at the third one, the irrigation to in this case rice or tea plantations is stopped completely. So TSMC has in total present in 3 science parks over Taiwan, and they're in Hsinchu, and they're using around 63,000 tons of water per day. And over all 3 sites, the consumption of water in 2019 was 63 million tons. Though the company did report that they managed to recycle 86% of this amount, they're still using incredibly large amounts of water to keep their production up. On the other hand, of course, that doesn't mean that the companies are not investing efforts into water recycling and environmental preservation. In the case of TSMC, it's really just very difficult to keep up with being environmentally very aware and keeping the production up and producing more and more modern chips. So on the left image here, we have an excerpt from Intel's CSR report. Intel is reporting on net positive water for 2 years in a row now. So this complete or total water withdrawal of 10.5 billion, in this case, of gallons per year, over the sum of water restored. Water restored is size discharge, plus water returned, which is basically related to different watershed projects, for example. So the ratio of these two would be then, or the other way around, would be 110%. So Intel seems to be doing a very good job in water recycling and being water net positive. Perhaps it has to do something with the locations of their manufacturing sites. They do report on a lot of on a lot of community projects, for example, in Costa Rica. Maybe it's easier to implement these kind of projects in such regions over the world. On the other hand, on the right side, there is an example from TSMC. TSMC seems to be falling behind their internal targets in 2023, where they were supposed to reduce the unit water consumption by almost 3%. They actually increased the same by 25.2%, and the base year was 2010. So they're trying to now reach the 23 target in 2024. But yeah, the goals just seem to be a little bit unrealistic, judging by their CSR reports. So water consumption, again, not really by technology nodes, but over the years from CSR extracts. So this graph is somewhat less conclusive compared to primary energy demand, which was mentioned a few slides back. It is interesting to see. Of course, for TSMC, it is the same. So the trend is increasing again. There is a visible spike after the company introduced 5 nanometer node. For the rest of the companies, the situation with the water consumption per processed silicon area is not really clear. However, this ITRS lines on the bottom part of the graph do show that the industry is really not managing to keep up with the ITRS recommendations. So this is just as an illustration for 1 centimeter square chip, which was realized in a 5 nanometer technology node. We require around 23 liters of water. 70% of that is reclaimed water and 30% is water intake. Okay, so these were the environmental indicators, well, mostly in terms of efficiencies, but what happens with the absolute numbers. So again, data from 4 foundries was investigated from their CSR reports. These are some of the major foundry players. Samsung was very much of interest. However, it was difficult to extract their data only for the foundry division. So for that reason, it was left out. The performance of the foundries was extracted for the period of from 2012 until 2021, so for 10 years. Processed silicon area obviously did increase a lot, almost 3 times. So the market expanded tremendously. Therefore, also the GHG emissions did double. It is maybe interesting to note that in this case, the scope 1 emissions did remain around the same value, around 3,400 kilotons CO2. What contributed to this growth of total emissions was actually scope 2, which means that factories were relying on second parties for providing the energy. Energy consumption in total increased 3 times, and the water intake increased 2 times. So yeah, this is maybe gives it's not a complete data. It focuses only on a few foundries, but still an interesting table to have a better overview of what the absolute values are. A little bit about carbon footprint, about CMOS chip. So this is a study which focuses on a little bit older technology node, 130 nanometers. The authors actually created a library of energy use, material inputs, and emission data at the process equipment level and also facilities scaled, and the data was normalized per wafer. They're looking into CMOS microprocessor with 6 and 8 copper layers. 300 millimeter wafer's supposed yield was 80%, and then die size is 11 by 11 millimeters. So from the literature, they did extract the process and equipment facility inputs. In this case, the data is presented for one particular step, CVD of ultrasilicate glass. Facility inputs are my apologies. So the first graph was actually extracted from the equipment manufacturer, which is taking care of the gas emissions of the material input and gas emissions after the processes and taking into account the abatement process on the machine level. The facility inputs are taken from another source, from the literature, as the authors reported, and then the library and the final result is this final graph split into devices for 6 and 8 layers. So this is maybe an interesting example to just show how these libraries can be created. However, there is one remark, that is that the global warming potential and the emission of the gases which are mentioned in this table and calculated do not relate to the final emissions, because the abatement on the facility level still has not been taken into account in this study. That was related to the front-end processes. Now a little bit on the 3D integration. Another case study where authors were looking into redistribution layers. So RDL consists of metal layers. Two materials were looked into, aluminum and copper. Then films for passivations were, well, here they call it mineral. It's actually silicon nitride and TiO2 material, and they compared it with polyimide. And then for the metal multilayer, they looked into two different types of depositions. One is sputtering, and the other one is electrochemical deposition. And the outputs produced by these authors is actually a relative ratio between these different steps in the production of RDL related to different materials, and then the environmental indicators that they focused on were acidification, water use, eutrophication, resource use, climate change. So based on these results, the most perfect or the most environmentally friendly combination would be use of aluminum line, organic passivation, and underbump metallization, which is deposited by ECD. In this case, this combination is, I think it has 76% better result compared to the combination of the other materials. So where does this stem from? Most notably from the use of of gold in UBM. So physical vapor deposition uses much more material compared to electrochemical deposition, though the authors did mention that a lot of material can be recycled from both of these deposition methods. Then another thing, for example, in case of mineral passivation, ecotoxicity is much higher because it uses TiO2. More energy is used for deposition and also for patterning of the layers because of use of C2F6 and so on. Another interesting example by Infineon, available online on their website. So Infineon is reporting on the overall carbon footprint of their different families of products. In this case, just as an example, we're comparing Optimus and Oryx microcontroller. So the categories that they do report on are PFCs and direct emissions, transportation, material, and energy. Then transportation can contribute less or more to the overall carbon footprint, depending probably where the device is assembled. Maybe it's tested on another side, so it's just traveling back and forth. Of course, another aspect that plays an important role is the size of the package. In this case, the microcontroller has a size about 25 by 25 millimeters, whereas the Optimus package has a size of 4 by 5 millimeters. So the overall footprint is also much less. When it comes to reporting in the material section, it is important to note that the backend processes are contributing very little to the overall environmental data, only up to a few percentages. And I think this was my last slide, so you can go on, Michael.
Okay, thank you. So, yeah, okay. So come to process-related details, mainly there for PFAS and PFCs. So let's look at the complete CMOS process or CMOS stack-up. So this is an example from Wikipedia. It's from around 2000s. But basically, you have the front end of line, including the middle of line, which makes the contacts to the transistor layers. Then you have the back end of line, which is mainly consisting of processes in the range ALD, PVD for the barrier materials, plating for copper for the UV, RIE, and probably in the lower sections also ALE. PCVD or PALD, so TIOS or low K dielectrics and CMP. In these process sequence usually is a kind of process and repeat to build up all these layers. And then the backend, I would say, which would incorporate this part, they have also probably a rerouting. So it could be a process and repeat sequence, or it could only be a spin-on. Usually used are here PI, PBO, PCB, PVD for the barrier metal, and then plating of copper lines or the UV, including also there then the bumps. And in some cases, especially for wafer level packages, they're also going maybe there in TSV formation or dielectric etch. I will come on one of the next slides to that. But basically, this was in the 2000s, the sketch. Now, more actual, also not completely modern chip looks like that. So you have much more metal layers. So that means the back end of line really process and repeat is getting more and more the focus, because especially there you have etching gases, etc. You have also there all the lithography steps. And these two are the main concerns when it comes to environmental harmful materials. So when we go first to the lithography, so it's a very important step all over the process sequence. So on the right side, I have a sketch of really the transistor layer until the middle end of line process. And there you can see for every step here, you need definitely the lithography and a very advanced lithography. But also when you go then to the back end of line, you still need a quite advanced lithography. So when we are speaking about modern nodes, you have more in the front end line, the EUV stepping. And then if you're going in the back end of line, you usually have something like the DUV steppers. And as you can see, I have here a sketch comparing the mask steps and also the lithographies that are used for them for Intel, Samsung, and TSMC for different node size, so 10 nanometers and 7 nanometers. Also in some cases 5 nanometers for Samsung. These are more or less the estimated counts, but you can see that the count of mask layers is increasing, and also the usage of the EUV stepper is increased when you go to smaller and smaller dimensions, because sometimes you then need quadruple exposure. That means you have 4 lithography masks combined to generate one layer of functionality in the transistor. So the EUV usage is massively increased there as well. And so to say the lithography is really the central and most defining process technology you have in the wafer manufacturing. But on the other hand, for that, you need a very, very good image print quality of the resists. And the specialty or the problem when you have, in some cases, failures at one step, sometimes the real failure can then only be detected after several steps. So it's a very crucial process sequence that the companies are very hesitant to change, because on the next slide, many of the components, or I would say chemical components regarding the lithography resists, or also PBO, PIs, having PFAS or are PFAS containing. And you don't want to change that in such kind of delicate process sequences too fast and too much. So they're very resistant to do that, because there are PFAS alternatives. But when you look at this graph, you can see that performance-wise, the PFAS containing materials are still the best. So there a lot of research has to be done to change that. And usually such kind of materials are developed over 25 or more years. So it's really hard to change those in the complete process chain. But anyhow, in some areas we have to start. And I guess some of those areas might be more in the back end, or might be then the packaging. And yeah, that's some large area where the research community has to act. The other one would be reactive ion etching or deep reactive ion etching. Usually you have kind of fluorinated carbon gases. I just indicated which steps, so also the complete back end of line, but also in several processes in the front end of line, you need different etch gases. Also for the packaging, if you want to incorporate some TSVs, you have to etch through the whole dielectric, and you have also to etch through the silicon. And usually you have these gases in production predominantly. In our case, we have mainly SF6. And they have very high global warming potentials. So people are really looking for alternatives, especially, for example, for TSV etching. We don't have really an alternative for the SF6. So the TSV generation is usually when you have a certain kind of TSV, I will show in the next slide, you will have to stay on these gases to go first through the dielectric, through SiO. That could be of a thickness of 10 micrometers. And then you go into the wafer that could be 100, 150 microns with different approaches. So we have either the via middle, we have the via last, or we have the via last from the backside. So the back end of line is now on the backside, flipped on the wafer. Usually when we are doing some work there, we are having a via last where we go through the back end of line, or we have the via last from backside approach where we go first through the silicon, then through the dielectric, and then on the contacting metal. That might look like that. And so therefore we have to start to look for alternatives. Usually when you want to introduce alternative gases, you need quite a long and intensive time for the research that could be more than 10 years to avoid or to replace some material. And then from the development, integration, and then really a manufacturing ramp up, there you have the ability to effect change. So really here in the development phase, it's a very, very crucial phase for that. However, there are not very many candidates that can be used instead of certain gases. So when we have now the PFC gases, so SF6 is missing in that for sure. There we really have not really a viable substitute for the fluorocarbon chemistries at the present. There are some gases that can be used, some pure fluorides diluted with some argon and nitrogen. So these are quite promising contact candidates. On the other hand, it's still not clear what are the byproducts afterwards. And this is just a table showing all the different dry etch chemistries, and also what's also very important for us is the chamber cleans afterwards. And on the right side here, you can really see how many years they see for the development for that. So that really means we have to start more in this direction to have, let's say, in 10 to 15 years, some substitutes running in the fab development. So when we conclude for the PFC gases, so we have to see, we need process optimizations. That could be something like endpoint detection to reduce the gas usage during dielectric etch, probably. We have to look for alternative process chemicals, for instance, to change to NF3 remote plasma cleaning instead of the C2F6. We have to see when we have to stay with SF6 as an etch gas, so what are the probabilities to get such kind of gas by using or recycling these. For example, here they're used as an insulator for high voltage circuit breakers. And we have definitely to look into the abatement that we minimize the amount that is going in the atmosphere. So with that, we come to the conclusion. So first of all, we tackled the clean room facilities. And there we have really to concentrate on recycling or refeeding of different materials like fresh water or the air supply. And then on the other hand, we have to see how can we do the abatement or the separate collecting of different waste materials that are not going directly into the water system. The other part is when you are constructing clean rooms, the problem right now still is that you really do not have a lot opportunities how to modularize such kind of clean rooms. You have, when you build a plant, you have really to plan that a little bit oversized for the future needs. We have also seen that when you have the data collection and reports for the environmental impacts, they are often missing the common framework. So the numbers of those reports are really not easy to compare on a first glimpse. And we also see that although significant efforts have been made to minimize the environmental impact in the IC production, the absolute values for the advanced nodes are still distinctly growing over the past years. And for things like lithography materials, chemicals or gases for etching, or also for plating, for example, in the back end, we have really to immediately start alternative materials because the commercialization and the implementation can take much more than 10 years plus. So with that, we say thank you very much. And now we are open for some questions.